Hi there, welcome to another edition of Bird Series Biologists Explain This. Today we'll be discussing the topic impulse transmission. We've been discussing previously, we began this nervous system series by starting with the parts of the nervous system, the branches, the peripheral nervous system, the central nervous system, and then we went ahead to discuss the different parts of the nervous system. We discussed neurons, types of neurons, how to differentiate and distinguish between the different types of neurons, and we talked about after that what we discussed and the issue of impulse generation. And today we'll be looking at how an impulse is transmitted along the length of a neuron. Come along with us and enjoy. Let's look at our learning objectives for this lesson. At the end of this lesson, you will be able to describe how nervous impulse is transmitted along a neuron and be able to also describe the meaning of saltatory transmission and be able to explain the role of myelin sheath in increasing speed of impulse transmission. Let's begin our discussion in details on how impulse is transmitted along the length of a neuron. Now, if we remembered what we discussed last time on impulse generation, we discussed the concept of the fact that you have local circuits, okay, between a depolarized region and the next or the neighboring or the adjacent. So that the synonyms you can use to remember this discussion. Whenever a particular part of a neuron is depolarized, it is that region that is depolarized. The remaining length of that neuron, those regions are still in a polarized state, meaning they are negatively charged. So what you see or play out is the fact that a local circuit, local in the sense that it's just in that region, it's not throughout. So what you have is that a local circuit is set up between the depolarized positive region and the next or the adjacent polarized negative region. Is much like when you have a battery. Just picture this in your mind's eye. When you have a battery, there's a positive end of that battery and the negative end of the battery, and if you connect these two ends with a wire, a current begins to flow between the two of them, because now you have set up a circuit by connection. So the issue of circuit comes in when you have a connectivity, a connection. So in a sense, when you have a depolarized region next to a polarized region, a circuit is set up. So what you begin to see is that sodium ions being positively charged, concentrated at that depolarized region, they begin to get repelled from that region and attracted towards the neighboring or the adjacent polarized region. And so you begin to see a drift where positive charge or units of sodium ions begin to get drawn. So they are being repelled from and they are being attracted to. Just look at those two words, from and to, from the depolarized region to the polarized region. And so what you begin to see is that just like we saw in the case of how an impulse is generated, they begin to cancel out the negativity that existed in the polarized region. Let's just look at this scenario we discussed the other time. It's like you have a party and then you've got 50 males and 50 females, and then you begin to have more males coming in. Okay, definitely it becomes difficult to pair the genders. I mean, you have more guys at the party and then you have fewer ladies, and it's going to be, there's an imbalance there. So the moment you begin to have positive charges moving towards the polarized region, they begin to build up the positivity in that region. That region begins to get gradually. So we talked about the fact that the polarized voltage is minus 70 millivolts. Okay, we said some scientists or some authors talk about minus 65, but it is not the issue. The fact is that it's negatively charged in a polarized state, and so you begin to see gradually the negativity begins to get cancelled out or neutralized. You get from minus 70 millivolts to 60, then to 55, and then to 45, then to 35, and then you get to the zero, and then it becomes more and more positively charged as more sodium ions are being drawn or attracted to the polarized region. Now, what we see play out is the fact that the depression in this region is boosted by more sodium ions diffusing down their voltage gated channel. So you have a boost because the ion, definitely not all the ions that you had in the depolarized region will be drawn to the polarized region. And so you have a boost in which more channels open and sodium ions diffuse in to help the effect that we want to produce, meaning to depolarize that region as fast as possible. And so, like we said, for you to have an action potential, you have to exceed the threshold. So what you are having is that you need as many positive charges as possible to cancel out the negativity that existed before in that region of the neuron. And then once you're able to depolarize to the extent of exceeding the threshold, you have definitely succeeded in producing an action potential in that region also. And so what you have now is that this depolarized region now has a circuit between it and the immediate next or the adjacent polarized region. Remember, this region that we are discussing was in a polarized state before, meaning negative, and then sodium ions that were repelled from the neighboring region came there, diffused there, depolarized that region, and so now this region is now positive, and there's a circuit between a local circuit between it and its neighboring region. So what we saw play out before is the same thing that will play out now. There will be repulsion of sodium ions from this region and attracted to the neighboring region, which is still or presently in a polarized state, meaning is negatively charged. So as you can see so far, an action potential along the length of a neuron spreads like a wave of depolarizations. What you have is, let's look at the analogy here in our mind's eye. Picture holding a rope in your hand and the other end of the rope is held by somebody else or tied to something. Okay, like you learned in physics in waveform, once you moved the rope up like this, you begin to see mechanical waves spread from your end to the other end of the rope. Remember, all you did was to move the rope once, and then the mechanical waves of the rope just began to move from you. You didn't have to do it again, no repetition, just once. So what you see is like that. Once a region of a neuron is depolarized, that depolarized region acts as the stimulus to depolarize the next region. And that region, now having become depolarized, depolarizes the next region. And this region now that's depolarized acts as the stimulus to depolarize the next region. So an action potential simply spreads along the length of a neuron in the form of a wave of depolarization. So a depolarized region acts as the stimulus to depolarize its neighboring or its adjacent polarized region. I hope you are enjoying this discussion so far. Now, having discussed how an impulse is transmitted along the length of a neuron, we turn our attention to the factors, or let's say the design or the arrangement such that the speed of an action potential can be increased. In other words, the essence of the nervous system is to aid in the responses of the animal to stimuli around it or in its environment. Just picture a prey having to run from a predator. The way nature has endowed both organisms is to ensure that if the prey is not able to identify the approaching threat, if you look at it, you've got predators are the prey. They've got this external pinna that's very large. If you look at an ordinary rat, look at it there, okay, they have this large pinna, which is the external air that can receive or perceive sound waves from a distance, meaning there is an approaching threat. And they've got their eyes in front, I mean, on the sides for all-round vision. So while they seem to be looking forward or straight, they can see from left and right sides like that. So they have their eyes rolling in a socket to be able to identify approaching threat. And importantly, they've got to be able to run fast. And so having sensed danger of threat of an approaching predator, the prey has got to outrun the predator, otherwise it will be eaten for food that day. The same goes for the predator. It's got to outrun the prey, otherwise it's going to starve for that day. And so there's this issue of what is known as rapid escape responses. Let me say that again. rapid escape responses, where an organism has to respond as spontaneously as possible to any perceived or imminent danger. And so we have on the slide here two key factors that can increase the speed of an action potential. One is the issue of myelination, okay, of the neuron, and secondly, we have the concept of giant axons. Let's keep enjoying the discussion. So let's look at first the issue of myelination of a neuron. Now, we discussed previously when we were discussing in the branches of the nervous system, we talked about cells that assist it that work together with the neurons. Neurons are the nerve cells that have been modified to transmit nerve impulses in form of electrical signals. We discussed that so far. And so we are looking at myelin sheath helping to increase the speed of impulse transmission. So the first thing is to realize that, or to remember or note that the role of myelin sheath is to increase the speed of impulse transmission. So myelination is going to cause an increase in the speed of impulse transmission. Now, if you look at it ideally, a neuron that's myelinated can transmit impulses as fast as 120 meters per second. That's quite fast. Okay, and so let's look at how this happens. Now, myelin sheath, like we said, is formed from Schwann cell, and Schwann cells, the membrane of the Schwann cell is modified to wrap around to form an insulation around the region of a neuron. And so remember a membrane is hydrophobic, hydro water, and then the phobic means to have a dislike for, to have no affinity with something else. So what you have is that when you have myelin sheath wrapped around the length of a neuron, okay, it insulates that region, meaning that region has become depolar, become insulated. And remember, for you to have electricity, okay, in your chemistry, recall that there are two key ways by which you can generate an electric charge. One is when you've got ions moving between electrodes. When ions move, that constitutes electricity. And then secondly, when you have electrons moving through a metal conductor, that also generates electricity. So of these two events, it's the issue of ions we are discussing. And so when ions move across the membrane, you are generating electricity in quotes. So in this context, when that region is insulated, ions cannot move. Okay, so that's what we have. And so if you look at the scenario now, you have several myelin sheaths along the length of a neuron. Now you can have as many as 250 to 300 myelin sheaths along the length of a neuron. So a sheath is not like an entire wrap. Okay, it's a series of individual sheaths formed by individual Schwann cells. Okay, and in between adjacent myelin sheaths, you've got a gap, a space called node of Ranvier. So that node of Ranvier is not insulated by myelin sheath. So you could have ionic exchanges between the extracellular fluid and the exoplasm of the axon. And so that's the picture in terms of the structural design of a myelinated neuron. So in essence, everywhere there's myelin sheath along the length of a neuron, there can be no depolarization in those regions, okay, because they've been insulated from ionic exchanges across the membrane in that region. And so no local circuits can be set up anywhere there is a myelin sheath. Now, a myelin sheath can have the length of about 0.1 micrometer to 20 micrometer. Remember, a micrometer is a millionth of a meter. That is 10 to the power 6 meter. So if you look at the scenario, that's similarly small region. Imagine you have like 250 to 300 myelin sheets. Multiply that by 20 micrometer. That can give you what we are discussing here, the picture in your mind's eye. So when you have So within that region where you have myelination, there are no local circuits. Let me try to explain these local circuits again, like can be clear in your mind's eye. Now, imagine you're sent on an errand from your home to somewhere else, and you met five of your guys. And every one of them that you met on the way, you've got a great, you've got to hail, fist bump, okay, Man U Chelsea, who won the last match, okay, the latest thing, the gist, the gossips. Remember those things, you were stopped 5 times on the way. Now compare this scenario with the case where you met nobody on the way. You just ran to buy what you were meant to buy, and then you just returned to your parents or whoever sent you on that errand. And look at the two scenarios. You met people on the way. Those were like local circuits because there were exchange between you and the friends or the acquaintances you met on the way, unlike when you just walked on the journey or on the path of the errand you were sent without having to talk to anybody on the way. So every time you have myelin sheaths along the length of a neuron, local circuits will not be set up in those regions, meaning local circuits cause delay. Let me put that clearly. What local circuits do, so imagine when an I was positively charged and I've got to help you to become positive charge like me. So a depolarized region helps encode its neighboring polarized region that is presently negative to become positive like it. And then when that becomes positively charged, depolarized now, it's going to have to help. Remember, ions have to diffuse from the depolarized region to the polarized region to make it depolarized. And then we talked about the boost from outside. We have silicon ions that fuse inside from their gold and voltage gated channels to boost the positive charges in this region. So you are building up the polarization effect. Now that event or those situations, they are causing delays. And it's those delays that myelin sheath is helping us to circumvent. In other words, everywhere there's a sheath, there will be no local circuit. The ions that are being repelled just simply move through the exoplasm of the neuron and then get to, so as they are moving, when they get to the node of Ranvier, that is the only region where there can be a slight delay because you are going to have to depolarize that region. Channels open for silicon ions to diffuse in, depolarize that region, the threshold is exceeded, and action potential is created. And then you have a move again, a drift of these ions. As they move again, no local circuits in the next myelin sheath region until they get to the next node. So what you have is that action potentials are limited to just the nodes. So what you see is that you picture it as if the impulse is leaping from node to node. That is what is referred to as saltatory transmission. Like you have a kangaroo just leaping or hopping, or you see the toad or the frog leaping rather than having to walk. Because if you had to leap, you save distances. But if you are walking, it's a much slower pace. So that's the scenario, that's the picture I'll be enjoying, and you're trying to visualize what I've been discussing so far on the issue of the influence or the impact of myelination in terms of increasing the speed of an action potential. So remember, the concept of this slide is the issue of saltatory transmission, which is the impulse leaping from node to node, because local circuits that could have caused delays along the neuron, they are not existing, or they are circumvented by myelination, that is an insulation of certain regions. And like I said earlier on, the myelin sheath is it has the size of about 0.1 micrometer to as much as 20 micrometer, and then you can have up to 250 to 300 sheaths along the length of a neuron. So look at the multiplier effect of many sheaths along the neuron. So the more myelinated a neuron is, definitely from what we have discussed so far, the faster will be the speed of impulse transmission along the length of that particular neuron. So, so this next slide is trying to remind us of what happens when you had a polarized state before the issue of depolarization. So you remember we talked about this carrier protein called NAK pump that pumps out 3 sodium ions from the exoplasm to the extracellular fluid on the outside and transports in 2 potassium ions, we said the result or the effect of NAK pump's action is to cause an imbalance of imbalance between the positive charges and negative charges. Remember, just imagine 3 against 2. It means that if NAK pump operates 10 times, you will have pumped out 30 sodium ions and will have brought in 20 potassium ions instead. That's a deficit of 10 positive charges. And so if you look at it, we said at rest, okay, I'm just trying to remind you of this stuff. And at rest, there is a balance between the positive charges and negative charges. Once NAK pump begins to operate, active transport using energy from ATP, it causes the imbalance. So I hope you understand this particular slide. Very interesting stuff. So we'll be looking at a couple of slides just to eh, let us understand clearly or to visualize what we've been discussing. This particular slide is talking to us about what you see when there's no myelination. So remember, ions diffuse out, ions are being pumped out and then brought in by NAK pump. So this is what you see. And so you can see the region that is depolarized there in the middle. You can see the sodium ions diffusing in, and then of course at the peak of action potential you see K plus channels opening, and then you see potassium ions having to diffuse out down their electrochemical gradient. And we come to this next slide that is painting a clear picture of the events happening when you are having impulse to be transmitted along the length of a neuron. So look at it. Look at that region to your left, the first diagram on the upper left side. You see that that region is shaded, meaning is depolarized, but you see that there's a boost, okay, in that region where sodium ions or sodium channels opens for sodium ions to come in to boost the effect of depolarization in that region. I can see the region that is yet to be depolarized in plain color there, just to show a distinction. And so you look at it when ions moved, so you can see the arrows. When ions moved from the polarized region, that next region became colored again to show that you're having a boost, and then the channels opening again. So what we are talking about is the issue of repulsion from the polarized region of sodium ions and then their attraction to the neighboring or yet to be depolarized region. And so you can see that the shaded portion is spreading, meaning you are depolarizing progressively. So we said an action potential is self-propagating. Just initiate it, it spreads on its own until it travels throughout the entire length of that particular neuron. So we see a much more interesting slide, okay, showing us the issue of myelination along the length of a neuron. You can see that here you have myelin sheath. Yeah, is referred to as a passive region, okay? No action potential. It's a passive because no activity, no ionic activities are going or occurring in that region. And where you have the node of Ranvier, that region is described as an active region because you can generate an action potential. You can see the machine indicated in blue recording the action potential being generated as the impulses are traveling along the length of the neuron. So we are discussing giant axons, which are in the range of a size of 1 millimeter. That's like the head of your pencil point, or you can just look at your ruler, just one line on your ruler. That's what they are. Is when you hear the word giant, it's not as if they are that big. They are not that as huge as the word connotes, but it's because when you compare them with axons that are in the range of micrometer, micrometer is in the millionth of a meter. That's 10 to the power minus 6. Okay, so when you look at the scenario and you're talking about something that is in millimeter, meaning it's visible. You can measure it with a ruler, unlike the microscopic ones that you cannot see because they are in the range of micrometer. So that's the scenario. And then, of course, giant axons were discovered in these organisms called squids. Squids are aquatic cephalopods, and so you see them, they've got these giant axons. And then the question is, how do giant axons increase the speed of impulse transmission? Now, these two scientists, Goldstein and Roll, they discovered what is referred to as this kind of transmission that you're discussing here now. And so the cable theory that Goldstein and Roll discussed has to do with what is referred to as cable theory. In other words, the speed of impulse transmission is proportional to the square root of the interior diameter, that is the size of the axon. So if you picture it in your mind, as the size increases, let's say the size increases to something like 4 units, for example, from 2 to 4. You can imagine that is if it was 2 before and it's now 4, find the square root, it's like a doubling. So the speed is increased because of the size. So that means that an organism may have neuron that is not myelinated but can have giant axons. So picture the scenario now where the neuron, the axon is large and also myelinated. Fantastic stuff here. That would definitely help the organism to be able to run very fast. I mean, to escape the approaching menace of a very hungry predator. And so, remember the issue of the cable theory, and then just imagine the scenario of the fact that the neuron may be large, like I said, not that huge, and also myelinated. But the point we want to say here is that myelination increases the speed much more than giant axon. In fact, if you have myelination, you can have a faster speed than you can ever achieve with just having giant axons. So please note that fact. Now we are gradually rounding off this very interesting discussion on impulse transmission. But before we are done, I want to give you a couple of self-assessment questions to ascertain that you've understood what I've been discussing so far. And so the couple of slides that you have ahead from this particular slide will be giving you a couple of questions to test your understanding on what you have learned. And I'm particular about A-level students, Cambridge A-level students, because this particular topic is very important, very core in your P4. And so if you can answer these questions, then you will have done fantastically well, and you are bold and courageous and confident approaching your Cambridge A-level examination. And so try these questions, like I always say, and then sending your answers. I'll be glad to assess and then discuss with you on your performance. So this one is asking us to describe how a spinal reflex arc. Just look at those words, reflex arc. You did something close to this in your O level. If you're an A-level student, and if you're an O-level student, you'll be able to attempt this question to an extent and explain why it is an advantage to an animal, a mammal. Okay, so reflex arc is important. That's what is. I'm just trying to help to interpret the question to make it easier for you, and then be able to explain the importance, the significance of myelin sheath in determining the speed of nerve impulse. Is very interesting. You should enjoy answering these questions. So try your hands on the questions on those slides, and then, like I always say, sending your answers to the WhatsApp number, my email number, my Instagram handle, my YouTube channel. I'll be very, very eager to work with you towards your examination. No matter the examination you're preparing for, we can work together like a team. Remember, we are here to help to ensure that you do fantastically well in those examinations that are ahead of you. And so I wish you the very best in your examination. Keep learning, keep practicing, and you'll be the best that you can be. See you next lesson. Bye.